Think about the following question. Choosing two positive integers, a and b, uniformly randomly. What is the probability that they are coprime? Namely, the GCD is equal to 1. I'll let you think about this question for a while on your own. The answer is 6 over pi squared. This number is approximately 61% by the following heuristic argument. Because I said this argument is heuristic, I guess I should also quote this word answer. And you will realize why I said so later on. To start with, let us investigate first what the meaning of uniformly randomly is. Let p be a prime. For any positive integer, a, we consider the residue class of a mod p. This number is taken from a set of all residue classes consisting of 0, 1 through p minus 1. Strictly speaking, I should put some bars over them to indicate that they are classes, not just single numbers. But I guess it should be very well understood by you if you know number theory, just elementary number theory. So I will omit those bars. Now, if a here is chosen uniformly randomly, then the probability of a being divisible by p, namely the probability of a having the residue class equal to 0, will be equal to 1 over p. Because if a is chosen kind of uniform randomly, then the chance of a mod p hitting 0 will be like just 1 over p, because this should be uniformly distributed in this set. And given any pair a comma b in this Cartesian product, still chosen randomly, uniformly randomly, the probability of them being divisible simultaneously by p should be equal to 1 over p squared. And let me write it another way. Let me write p dividing the GCD of them. This probability is expected to be 1 over p squared. So here I use a notation, this bold p, to denote any probability. Strictly speaking, there are different probabilities, because this guy is supposed to be in this product space. Okay, let me still use this product notation. So the probability of this pair not simultaneously divisible by p will be equal to 1 minus 1 over p squared. Since this is a complement event of this. Okay, now, based on this meaning of uniformly randomly, the probability of the pair A, B chosen uniformly randomly of being coprime will be equal to the product of the probabilities of them not divisible by any prime number, namely the product over P ranging from the set of all prime numbers of 1 minus 1 over P squared. And you can write this another way as the reciprocal of the product of 1 over 1 minus 1 over P squared. So they are equal. And this, by the Euler's identity, will be equal to 1 over zeta 2. So this is by the Euler's identity. Here zeta is a famous Riemann zeta function. This guy will be just 1 over the summation from n equal to 1 to infinity of 1 over n squared, which is 6 over pi squared, by the classical result of the computation of the infinite sum of 1 over n squares. This was done in, for example, in Fourier analysis. Okay, now, how do you like this argument? If you think about this question really rigorously, you probably don't like this argument. Because, for example, we were not very rigorous at this point. When we're taking the infinite product of those probabilities of a pair not simultaneously divisible by P. Here, we were expecting that those events that the pair A, B are not divisible by different primes are kind of independent events. But are they truly independent? So let me carefully write this down. This argument is not rigorous, since the events A sub P in which the pair A, B cannot be simultaneously divisible by a prime number P. Those events are not necessarily independent. However, what is even worse is that we do not even have a well-defined probability on the space n cross n. For example, if I take in the sigma algebra on this space to be the discrete sigma algebra, namely every singleton is measurable, then what is the probability of that singleton? If the probability of every singleton in that case is 0, the probability of the whole space will be 0, which is absurd. So the probability on this space must be very weird. Maybe we cannot even take that sigma algebra to be the discrete sigma algebra. This is very weird. So let me highlight this sentence. And now at this point, you might even want to question the word uniformly randomly and the word probability. Is there a way to really make sense of those two words and make an argument that is truly rigorous, not only to amateurs, but also to professional mathematicians. And that is what we are going to do in this video series.